welcome to FRQ number 5 for set number 7. Okay, so number 5 gives us this situation. I went ahead and labeled my tensions. Draw my arrows. Okay, so let's go ahead and get into it. Part A wants us to calculate the angular acceleration of the pulley. Okay, so we know that we're gonna have to use torque. So let's go ahead, write that out. So torque equals F perpendicular times R. It also equals I alpha. Okay, so for now, what we're gonna do is we're just gonna keep expanding this, and then we'll go ahead and find our tensions just to keep our work nice and organized. Now, I have a feeling this video is going to be pretty long just because there's a lot of writing in this. Okay, so looking at our diagram, T1 is going to be the force that pulls, so that's going to be our biggest one. Remember, we want to do T minus, or big minus small, so then you have T2, and then it also tells you a frictional torque, and we're going to go ahead and subtract that as well, and that's going to be equal to, okay, so now we're looking at our I omega, or not I alpha, excuse me. Okay, so we know the coefficient, or C, for a pulley is 1/2. Okay, and it tells us mass is m/20, and then that's r squared, and alpha becomes a/r because you have a equals r alpha, and when you rearrange it, I was gonna say remove it, rearrange it, you get alpha equals a/r. So we go ahead and plug that in right there, because when we go and find variables sort of for our tensions, we're using newtons, and it's just easier to convert everything. You'll see, it's just easier to convert it, and then at the very end convert it back to angular. So with that, let's keep simplifying as much as we can. Okay, it tells us mass is 5, and then r cancel out there, and it tells us that the radius is 10 centimeters, and 10 centimeters equals 0.1 meter, and then a, let's keep simplifying. Okay, so we're gonna go ahead and multiply all this. So oops. Okay. Okay. So at this point, oh no, we can keep going. One more. So r, we're gonna plug in r everywhere. Okay, now what we're gonna go ahead and do is find our tensions so we can plug those in. Okay, so looking on this side, we have an effigy and a tension. So on this side, when you set up your F equals MA, so you're gonna have F is G minus T1 remember big minus small, is equal to, so that's m over 2, so m over 2a. And what we're going to do is move that around so it's solving just for t1. So 5 divided by 2 is 2.5a. Okay. And then let's see, t1, so that's 2.5 g minus 2.5a. 2.5 times 9.8. 24.5 minus 2.5a is what we get for t1. Okay, let's go ahead and find t2. So looking just at t2, you get t, again we're starting f equals ma. The only force there is t2, so you get t2 equals ma. So t2 mass is 5a. Okay, so now we can go ahead and plug those in over here. So t1, so 24.5 minus 2.5a times 0.1 minus 5a times 0.1. Okay, so this is why I converted alpha to a, just because these our tensions are in translational A, and it's just easier that way. That way I don't have to go in and convert it over here. I can just convert it here, and then at the very end just convert it back. That's why I did it that way. It's just a little easier. Okay, so now what we need to do is distribute, and all you do is you just move over the decimal point. Oops. Okay, so from here you're just gonna go ahead and combine like terms. So okay, now we want to move this over so we can get a by itself. Okay, and you get 3 meters per second squared equals a. Okay, but the question wants angular, so we're going to go ahead and convert it real quick to angular. So again, we have a equals r alpha. To get alpha, you just get alpha equals a over r. So 3, and our r is 10 centimeters, which is 0.1 meters. So 3 divided by 0.1 gets you 30 rads per second squared, and that is your angular acceleration. Okay, so B, calculate VH of the hanging block after it has descended D, which is 2 meters. Okay, so just going to go ahead and set up common form for that. 2a delta y equals bf squared minus bi squared. Okay, and plug in everything. So 2, we already found a. 3, our delta y tells us is 2. Okay, and it starts from S, so there's no vi. So vf, they want us to call it vh, so I'm just going to change that. Okay, so 2 times 3 is 6, 6 times 2 is 12, vh squared. Meters per second equals VH. Okay. So now it wants us to calculate the tension in the hanging mass, which is this one, which I call T1. So, okay, so we have our T1 right here. We have a little function for it, equation for it. So we're just gonna go ahead and write that, and I'm gonna change the 1 to h because that's what it says in the problem. It calls it th. So that's equal to 24.5 minus 2.5a, and we found a as 3. Okay. Get 17 newtons. So tension in the hanging mass is 17 newtons. Okay, so now we are given kind of a similar scenario, but sort of like kind of a lot different. So now what we have is a rope, and part of it was hanging off, and then slowly more and more of it started to hang off. So part D wants us to determine an expression for the force of gravity on the hanging part of the rope as a function of y. Okay, so so we're just gonna set up newtons. So now the only force there is F of G. Go to MA. Okay, and it wants us to do it as a function. Okay, so when we write, this needs to be mg, excuse me. F of G equals mass times gravity. Okay, so what we're looking at here is that only a portion of the rope has fallen. So really we need to find, we're using like the mass of that portion of the rope. So we need to write it that way. So it's going to be m times y over L, because y is the small part of the bigger length, times g. And then just go ahead and simplify this. So it's going to be y over this weird. So it's supposed to be, yeah, so y over L, and then you get MYG over L equals F of G. Because we're kind of looking at it as if it's like the portion of the rope. So E, so see, I think I'll have enough space here. Derive an expression for the work done by gravity on the rope as a function of y, assuming y is initially 0. Okay. So, work is the integral of force. Normally it'd be dx, but in this case it's dy. So from there we kind of just plug in everything that we know. Okay, so you get, this is going to be f of g, this will stay dy. Okay, so now we plug in f of g that we found, which was myg over L, and then we still have our dy. Okay, and then I need to be writing this. Okay, so now we can pull out our constants, things that can't be changed. So it's going to be m, g, and L. Okay, and if you remember, when you integrate, you can do that little trick. So let me write this real quick. Okay, so it's going to be it's supposed to be an L. Okay. Okay, so you can do the little trick where you integrate. So you would add an exponent, so this would be 2. So this is a 1, and then you'd add an exponent, so that'd be squared, and then you would divide by whatever that new exponent is. Or I should be doing that here. Right here. So you would add 1, so it's 1 plus 1, and then that'd be divided by 2. That's the little trick. So it would be y squared over 2. And then you can just go ahead and combine it, simplify it. And that gets you work. Okay. And finally, I'm going to just do part F right here. Hopefully I have enough room. Derive an expression for the speed of the rope. Okay. So what we're going to use here is the work kinetic energy theorem. So what that is work equals, or sigma work equals change in KE. Let's go ahead and expand that. So change in KE means KEF minus KEI. Okay, and we found work, so let's go ahead and write that in. Y squared. Okay. So we know that the system is at first at rest. Yes, released from rest. So that means there's no KEI because it's not moving. And that means we just have KEF, but it wants us to say V as VR. So I'm gonna write VR squared. Okay. Looking here, we can cancel out mass. We can also cancel out this 2 because this 2 here signifies that it's a 1/2. So then you're left with gy squared over L is equal to VR squared. Okay, so we're gonna square root that. So then that would mean the y would go on the outside because it's squared, and when you square root that gets rid of it. So then the y would go on the outside, and then it'd just be g over L. And that concludes FRQ number 5.